In Module 7, we are going to cover Chapter 7 in our textbook, and we're going to be studying flow past immersed bodies. And what flow past immersed bodies means the study of external flow around different shapes, essentially. Okay, and we're going to be looking at the type of flow that looks something like this. So let's say we have, for example, a sphere in air, in open air. We would analyze the flow around the sphere by looking at the streamlines and by looking at what happens in the wake, so what happens in the back. And there's really three different parts that we're going to be interested in when we study external flow. We're going to be interested in near body flow, which is our flow next to the body, and we're going to be interested in studying the viscous effects of this near body flow. Okay, so that's flow that's very, very close to the body, highlighted in red here. So we're looking at the flow of what happens around the body, very, very close. The next part that we're going to be interested in is what we call the wake. And the wake is usually the region, I'll show it in green, the region that is behind the body where the flow is complex and reconnecting together from the top side, the bottom side. This is usually called the wake. And in the wake, we're also going to be interested in these viscous effects. So we're going to have to come up with a way to study the viscous effects close to the wake. We're also, thirdly, going to be interested in flow far from the body. And with these three put together, we essentially get a full flow field. Okay, now the flow far from the body, we're going to assume that since it's not in contact with the body and it's far away, so it would be somewhere here, for example, at the top or somewhere here at the bottom, this is going to be assumed to have an inviscid condition. So we're going to assume that this flow is actually inviscid. Okay, now the big difference between internal flows such as our pipe flows in Module 6 and flow past immersed bodies or external flows is that we can say that external flows are unconfined and free to expand. So they have unlimited room to expand, and that means they don't get compressed in any way in the bigger picture far from the body. Okay, so we're going to be studying different experimental tests and different simple shapes that we can understand from an external flow perspective and try to attach equations to these flows. And the simplest geometry that we can study is called a flat plate. So if we have a flat plate within a flow, it becomes easier to understand. Okay, so the first thing we're going to look at is some geometry effects that occur due to the flow going around a body. So geometry effects allow us to use boundary layer theory. And we've discussed boundary layer theory a little bit in our previous chapters already, but boundary layer analysis can be used to compute viscous effects near solid walls. So in the same way as in Module 6, we're going to be able to come up with an equation to try and understand how the flow works next to solid walls. And we know that when the flow is next to solid walls, we have a lower velocity as we get closer and closer to the wall. And what we're going to do is we're going to patch this boundary layer. We're going to patch it. Okay, this is a term from fluid mechanics. We're going to patch these boundary layer flows to inviscid flow, which is our far field essentially. Okay, now one thing to note is that as the Reynolds number, and now we're going to use a sub x in our Reynolds number. Okay, we have a sub x because we're not using the diameter of a pipe anymore. We're now going to be using the distance of a plate or the distance of certain geometry. Okay, so it's going to be Reynolds sub x now. So as Reynolds sub x gets higher, we can say that patching gets easier. And this can be shown in the following figure. So I'm going to copy a figure over. That shows us two different cases with two different Reynolds numbers. So we can see that here we use Reynolds sub L, okay? So because the distance x is thought to be L, so it's the distance all throughout. And so this could be written as Reynolds L or Reynolds X. And we can see that we have two different cases with one low Reynolds number and one high Reynolds number. So here in the figure, we have a flat plate. Okay, so this is what a flat plate actually looks like in our experimental test. When we have a very, very low Reynolds number, such as Reynolds number of 10, okay, so we have a very low velocity, a very viscous fluid, we see that our inviscid flow occurs at the outside of our flow. We see that we have inviscid flow determined by a capital U. Okay, we have capital U here, and anywhere from here to the middle, we see that our velocity is not completely developed. Our little u, our local velocity, is not equal to u, it's less than u. Okay, and we see that this viscous region is actually a very large region. Okay, and we can see that the viscous region starts directly at the start and it actually extends out to even before our plate. So think of this as if honey was flowing past a flat plate or a flat edge, and you would just have honey sort of dripping along this flat plate. You could realize that you have a very big viscous region, and then the inviscid region would be very far away from that flat plate, okay, where the flow is not affected at all by this flat plate, okay? Now, in another instance, if we think of air going past a flat plate at a very high Reynolds number, meaning that we have a very fast flow or a flow that is with a very low viscosity, we see that the effects are much smaller. We initially have a laminar boundary layer that forms, and then eventually we have a turbulent boundary layer that continues to form. And we can see that our actual viscous region is very, very small, and we reach our terminal velocity very, very fast away from the plate. Okay, now one of the things that we see though is that the layer or the boundary layer, okay, we can call this the boundary layer or the viscous layer, actually increases with distance. Okay, so it does increase with distance as you go along the plate. And the reason will be explained later, but essentially we have a growing boundary layer because we have more and more effects from the wall slowing down the flow essentially. Okay, And what we can also see is that we initially have a laminar boundary layer and then a turbulent boundary layer. Okay, we start with our laminar boundary layer that ends somewhere here, and then we go into turbulent boundary layer. The reason why that is because if we look at the equation for Reynolds number, the equation for Reynolds number now is going to be different. It's going to be defined differently as in our pipes. It's going to be equal to U, our terminal velocity, times X over the kinematic viscosity. And the X is the distance in the X direction. Okay, so it's the distance along the plate. So we can say that as X goes up, so X increases as you go further down the plate. So that means that as you go further down the plate, your Reynolds number is actually increasing. And if the plate is longer and longer and longer, the Reynolds number keeps increasing more and more and more. So the Reynolds number is now a function of how far you are onto the plate. And if you remember, the higher the Reynolds number, the more turbulent flow you have. So that's why at the very start of the plate, in the first part of our flow, so in the part from here to here, okay, from the start of our plate to the end of the laminar boundary layer, we actually have a Reynolds number that's laminar. Okay, once we pass that level, we have a Reynolds number that shows that we have turbulent flow. And what's really important to note too is that the transition Reynolds number, because the equation is different, because the equation is now with our distance and not our diameter, the Reynolds number of transition is going to be different. All the numbers from the pipes are not going to be the same. So the Reynolds of transition is not going to be 2,300. Okay, so we'll see what that value is in a little bit. Okay, so in 1904, Prandtl, which we've talked about before in the class, said that the boundary layer thickness, and he called it delta, is defined where u, our local velocity, so where our little u, our local velocity, is 99% of the external velocity. And the external velocity in plate flow is usually called a capital U. Okay, so this is a capital U. Okay, and Prandtl also derived from his boundary layer works, derived that for flat plate flow, he said that his delta over X from experimental testing was equal to the following equations. He said that it was equal to 5.0 over Reynolds X to the 1/2. Okay, so we can see that it's Reynolds sub X to the 1/2. This is for laminar flow. And for turbulent flow, he found that it was equal to 0.16 over Reynolds X to the 1/7. Okay, and he defined laminar flow to be occurring between 10 to the 3 Reynolds X to 10 to the 6 Reynolds X. And he said that turbulent flow was any Reynolds above 10 to the 6. Okay, so we can see the numbers are completely different. our transition region is occurring around 10 to the 6th. And anything above 10 to the 6th could be considered turbulent. Anything below 10 to the 6th could be considered laminar. And when you're close to 10 to the 6th, you can assume that there's a little bit of a transition region, and it might be a little bit more complicated to work. So some specifications on this equation. This term right here is the thickness of the boundary layer on one side of the flat plate. So this equation is valid for one side of the flat plate. So if we look at our experiment here before us, if we erase the lines on the left, this boundary layer thickness is essentially delta would be on one side, not both sides. And the statement that he said boundary layer thickness delta is defined where u is 99% of the external velocity. It means that if our local velocity is less than 99% of the external velocity, we're still in this boundary layer. Okay, so as soon as we feel an effect from the wall on the flow velocity, we can count that as our boundary layer. Okay, and the x value, so the second value, the x value here, is the distance from the start of the flat plate. So depending where we are on the distance in the flat plate, we're going to have a different delta, essentially. Our delta is going to be changing with the distance of the flat plate if we know our Reynolds number, okay? So that's going to be very important. Okay, so we can also say that in general, boundary layers are very thin. Okay, so very thin boundary layers have, we can say that they have negligible effects on the inviscid layer. And for this, we can say that if we have a very thin boundary layer, we can also say that the pressure distribution around on the flat plate or around the flat plate can be computed from inviscid theory. So we do not need to use viscous theory if we have a very thin boundary layer around a flat plate. So if we look back at our diagram above here, we see that we have a laminar boundary layer and a turbulent boundary layer, and they look pretty thick compared to the flat plate. What we need to understand is that this thickness is very exaggerated. Okay, so the thickness shown is actually pretty exaggerated. Okay, so the actual thickness in real life is very, very, very small. Okay, so that's important to note. Now, what we can say is that these statements here are applicable, they're okay for slender bodies. We can use it for slender bodies. And what we mean by slender bodies are bodies that are parallel to the stream and are thin, such as, for example, a wing of an airplane, or a body that doesn't have much frontal area. Now, the opposite of a slender body is a blunt body. For blunt bodies, we have a much bigger effect of our layer that is viscous. Okay, we have a much bigger effect from viscous layer. And for blunt bodies, the analysis becomes more complex. So essentially what we're saying here is that for flat plates, we have a very easy boundary layer theory that we can understand and use, and it's pretty easy to understand. For blunt bodies, when we change our Reynolds number and when we have different conditions, we can have some big problems happening. And we're going to look at figure 7.2, which I'm going to copy over right now to show you the example of what happens to a blunt body compared to a flat plate body. So a flat plate body has a nice, simple growing boundary layer that's very simple to analyze based on the Reynolds number. Now, a blunt body has this that we can see here. So in A, we have an idealized explanation of how blunt body could happen. So this is ideal, okay? This is not real, okay? And we can see that ideally, this sphere or this ball in space, okay, has flow going around it, and we can see the flow comes back, and this boundary layer and wake are very well organized, and we get this beautiful flow that is essentially the same as what you would get for a flow on a flat plate. So if we had a flat plate, you would have the same type of flow. You have no disconnection, everything is working fine, and everything is great. Now, in real life, this doesn't actually occur. What happens is in the actual picture, which is B, we actually have a separation that occurs right here. So our flow cannot stick to our sphere back to the middle and go like this. What happens is we have this wake effect being created where the separation occurs. So we have this region called a wake where separation occurs. And when separation occurs, it makes it a lot harder to analyze analytically. Okay, so moving forward from that, what we can say is that blunt bodies are much harder to understand. And so what we're going to do is we're going to try to understand them in the best way we can, but we're going to start with flat plate analysis to come up with equations that we can use, and then we're going to have to somehow figure out how to analyze much more complex flows with some correction factors and some definitions of drag force and coefficient of drag, essentially. Okay, and through experimentation mostly. Okay, so now let's look at momentum integral estimates. And the momentum integral estimates are there for us to make some assumptions on and some calculations on what would happen in this boundary layer and how growth of a boundary layer can be analyzed. So I'm going to copy over another figure from our handout, which shows us the growth of a boundary layer on a flat plate. what we can say is we can see that in the figure we are shown that the thickness is exaggerated. So what we can say about this wall is we can say a few things. So we can say that a shear layer, visually, we can say that a shear layer grows along the flat plate and the flat plate is going to have what we call a no-slip wall condition. Okay, so what the no-slip wall condition means is that we have no slip on the wall, therefore our wall is not moving with the flow. It's stopped. It doesn't move, and if it doesn't move, it means that the velocity along the wall of U is actually equal to 0. And we have this shear condition that's happening through shear stresses in the flow through our viscous definitions from back in earlier modules. And we can say that this no-slip condition retards the flow. So it slows down the flow. Okay, we can also see in this diagram that we have at x equals 0, we actually have a velocity profile that is perfectly straight. We have capital U everywhere. Okay, so here on the left, we have capital U is coming in straight. And we see as we go along the flow, again, this is exaggerated, we start getting this profile of velocity that is lower than our terminal velocity due to that shear stress happening. So what we can say is that at this point here, okay, at this x is equal to L, at this point here, at x is equal to L, we can say that U, we can define that in this diagram, U of xy, so U is a function of x and y, okay, because the local U changes with the x because the boundary layer gets greater, and it also changes with y because the further away you go from the wall, the faster the local U. And we can say that uxy merges with our inviscid flow, capital U, at a thickness y is equal to dx, okay, or delta x. And this delta is the boundary layer thickness, okay? So the boundary layer thickness is a function of x, and we know that uxy, as we go along, merges at a thickness y is equal to delta x. Now, if you want to go into more detail on this, we can look at, so what we're going to do next is we're going to look at a momentum integral relation, and we have that d of x is equal to the density times b over the integral from 0 to dx times u of u minus u dy, okay? And this momentum integral was defined in example 311. So if you want to go back to chapter 3, you can look at example 311, where a derivation for this dx is given. We find that this dx is called the drag. Okay, so it's a drag force. Okay, and we know that B is the thickness of the plate into the paper. And we are doing this integral on a constant X line. Okay, so we're essentially doing the integral along a constant x, and we're just looking at the integral of momentum as a function of the height, pretty much. Okay, so you can look at example 311 to see how this equation was derived, but we can use this equation to understand how the drag force is applied to a boundary layer. Okay, so in 1921, Kármán derived that dx could actually be rewritten as, the drag x could be rewritten as equal to rho b u squared times theta, where theta was a new term called momentum thickness. So he called this term momentum thickness, and the momentum thickness was the integral from 0 to delta u over u times 1 minus u over capital U dy. So he just rewrote the equation in slightly different terms so that we could analyze it slightly differently. Okay, and momentum thickness is therefore a measure of the total plate drag. So what Kármán said is that the drag could be written as a function with rho b and u squared being constant, was now a direct function of this new term called momentum thickness. Okay, they're directly related with each other. And what he also found out was that the drag also equals the integrated wall shear stress. So if you take all the shear stress on the wall, you can also say that the drag from a different perspective is also equal to the thickness times the integral from 0 to x of tau w as a function of x dx. So if you sum essentially all the wall shear stresses, you would get an equation for the drag. And you can rewrite this also as the differential of d over dx is equal to b times tau w if you rearrange it. Okay, so we can write, if that's the case, we can also write that dd over dx is equal to rho b u squared times d theta dx. And we can go one step further. Now that we have two equations with two different terms, we can equate these equations, cancel the b's, and we can say that our wall shear stress is actually equal to rho times u squared of d theta dx. And this is a valid equation for laminar and turbulent plate flow. Okay, so that's boundary layer theory derivations to some extent by combining the equations for the drag force or the momentum equation along a velocity profile, essentially. Okay, and so this is also called the Kármán momentum integral relation. Okay, so this is called the Kármán momentum integral. Okay, and from this Kármán momentum integral, there's a bigger derivation in your book, but there was, with further derivation, he was able to come up with an equation for the desired thickness of an actual boundary layer that you would want. So the desired thickness of your boundary layer. So he said that through some derivations, d over dx would be equal to 5.5 over Reynolds x to the 1/2. Okay, and this is a term called the desired thickness estimate. And it is approximate, and it's part of the momentum integral theory. But it's actually pretty accurate. If we compare it to the known solution that Prandtl came up with of 5 over Reynolds x to the 1/2, we see that for laminar flow, we are only 10% higher than the exact solution. So by studying his momentum integral and doing some derivations, he was able to find that his delta over x mathematically would be equal to 5.5 over Reynolds x to the 1/2, which is 10% higher than 5 over Reynolds x to the 1/2, which was found experimentally through an exact solution. Okay, in the same way for the skin friction coefficient. So the skin friction coefficient is essentially a measure of the skin friction and non-dimensionalized. We have that CF is equal, so CF is the skin friction, is equal to 2 tau W over rho U squared, according to Kármán's momentum integral theory. And we can rewrite this as 0.73 over Reynolds x to the power of 1/2. Okay, now this is also 10% higher than the exact solution. And the exact solution for skin friction coefficient found from experimental data is 0.664 over Reynolds x to the 1/2. So we can say that all of the above equations are for laminar flow. Okay, so this equation right here is for laminar flow. This is also for laminar flow. And the two equations above are also for laminar flow. So all of it was derived for laminar flow. Now, if we go further than this, we can also say that a boundary layer has to have some way to be judged as thin or not. Remember, if we have a thin boundary layer, we can use boundary layer theory. If we don't have a thin boundary layer, we cannot use boundary layer theory. Okay, so we're going to say that a boundary layer can be judged as thin if the ratio of delta over x is less than 0.1. So it has to be less than 0.1 in order for us to use the boundary layer theory. Now, we also know that the exact solution for delta over x, if delta x is equal to 0.1, we know that the exact solution is equal to 5 over Reynolds x to the 1/2. So that means if we rearrange the equation, if we rearrange this side of the equation, we can find that Reynolds x should be equal to 2,500 minimum in order to have a boundary layer considered thin. So that means that if Reynolds x is less than 2,500, boundary layer theory fails. The theory cannot be used. So it's a good way to see if the boundary layer theory can be used. Now, from 2,500 to Reynolds x of 3 times 10 to the 6, we can use boundary layer theory. Okay, for laminar flow. And upwards of 3 times 10 to the 6, the Reynolds number is much larger, and we do not use the laminar boundary layer theory anymore. Okay, so let's look at the next thing, which is displacement thickness. So in this next part of the lecture, another interesting effect of the boundary layer is it's essentially we can rewrite the boundary layer thickness as a new term, essentially. Okay, so we're going to derive a new way of writing our boundary layer thickness. And this is sort of a shortcut that we can use to define what is happening if we do some shortcut analysis. So some scientists realized that, I'm going to copy over a handout picture, but some scientists realized that we could actually do something very interesting with our displacement thickness. Instead of trying to analyze our system and trying to find our u as a function of x and making it pretty complicated to analyze as we go along the path, what they actually figured out was that if we have a velocity u coming in to a flat plate at all the same velocity, they realized that as the flow came into the path, they realized that this height of the flow was actually going to increase as you went along the flat plate. And they realized that this height of the flow actually increased by d star. Okay, now what is the reason for that happening? So we have an initial flow that we can say has a height h, so we're going to assume that the initial flow comes in through a height h. And after a while, we see that this height increases. Why does this height increase? Well, the reason why is because we have a mass flow rate in here and a mass flow rate out here. And we remember that if we look at our boundary layer, and that's if we look at our flow just in, if we look at our U flow, we can say that our whole flow is actually going to have m dot in is equal to m dot out. And what we notice is that the velocity in is high from 0 to h. So it's a high velocity from 0 all the way to h. Now, in our outflow, we actually have lower velocity in the part below here. We have lower velocity. And then eventually our velocity gets high again. So if we look at our equation, we can say that this is equal to rho A1 V1 is equal to rho A2 V2. And we can say that the average velocity coming in is higher than velocity 2. So V1 average is greater than V2. Okay? So if V1 is greater than V2, that means that V2 is smaller. So in order to conserve mass, the only way to conserve mass is to make area 2 greater. So that's why the y increases. Okay, so y, instead of being equal to h at 1, so at point 1 we can say that y1 is equal to h1. At point 2, y2 has to be equal to h2 plus this new term called d star. We're going to call it d star, where we have an increase in thickness. So we can say that flow increases in thickness to satisfy mass conservation or continuity. Okay, so pretty interesting understanding that as you move along, you have a greater displacement thickness. And what the scientists said was that this d star, or this change in height, was actually now, so this boundary layer thickness, this d star, could be equal to the integral from 0 to delta of 1 minus u over u dy. And through dimensionless analysis and some approximations and some experimentation, they actually found that this value delta star was approximately equal to 1/3 of delta. Okay, so 1/3 of the delta is d star. And d star over x could now be equal to 1.83 over Reynolds x to the 1/2. But it doesn't stop there, because something very interesting happens. If we look at this d star, we can actually simulate our flow by saying, if the flow goes up by d star, instead of having a flow profile that looks something like this, if we know that mass is conserved and we know that the flow has moved up by a certain amount d star, we can redraw it as if there was a gap at the bottom d star, and then we have a straight flow of the same height as before, of the same height y as before, with a straight flow. And this would give us the same mathematical representation of our flow. So you can see it better drawn here, but essentially what we have is on this left side here, we have an equivalent simulated effect from the d star. So if we know our u and we know our d star, we can say that at our d star, the simulated effect has no velocity, and then everything was shifted up a little bit. Okay, so it's not a real representation of the flow, but it gives us the same approximation of the mass flow rate or the velocity of the flow, and this shift that we have upwards of the flow. Okay, so a kind of a neat observation, and you can read more about it in the book if you want to. And you might have some problems with D star given in your study problems or in some of the examples that we will do. Okay, so we're going to conclude our first part of Module 7 here, and in video 2 of Module 7, we're going to be analyzing boundary layer equations and looking at how we can use our boundary layer equations a little bit further.